I can cancel the 2's, huh? Yeah? Okay, let me get rid of that. And then this right here is just square root of u, but u is 1 minus pi squared x squared. So as a recap, we did integration by parts, which got us to here. This integral required substitution. That substitution took us all the way to here. That piece goes here. So now I go back to this, and I say this is equal to x arc sine pi x minus pi times, this integral is this, right? So negative 1 over 2 pi squared, square root 1 minus pi squared x squared plus c.
Yeah, we got rid of the 2.
Oh, I did get rid of the 2. Thank you. Thank you, whoever said that. Guess there's one more thing we can do. This will become a plus, and then a pi and a pi cancel, so we're there. So the antiderivative of arc sine of pi x, which looks, it just looks so, you know, so gentle and nice, right? Turns out to be this. X arc sine of pi x, and then minus minus is plus, so plus, then the pi and one of those cancels, so 1 over pi, and then this root right here. Root 1 minus pi. How about I put it back like this? Is that okay? You can leave it as pi squared x squared, but I just put it back like that. And then plus c. And of course you could check it, but I won't.
So if pi was anything else, like any other number, you would just, where all pi occurred, just put that other number. If it was 2x instead.
It should, yes. Like we could have done this in general and just done like arc sine of ax. And it most likely would have been, you know, a here, a here, a here.
So what you're saying is the integral of any arc sine is normally pretty.
Oh, yeah. Yep. And let me see, you have your formula sheets, may I? Is it on here? It is not. It's in the book, though. I'm sure that the formula sheet that you have that I provide online stops on page 7, but if you have the rest of them, there's page 8, page 9, and yes, it is here. Formula 87 is the antiderivative of arc sine. But we're not going to use a formula for that. We'd actually have to work it out. The formulas are just the basic ones. But if you ask yourself, like, where do these formulas come from, right? That's where these are where they usually come from. Good job, Mohammed. Let's move on. This will probably be our last example. Let me see how I'm doing here on these. All right, here are the problems that I was supposed to do today. So let's kind of just, I didn't do exactly this, but let's just kind of look at it. The first type that we did, we just had to use integration by parts one time, and it was all over, right? Everything was beautiful. This arc sine of pi x we just did, right? This is not such an obvious integration by parts because one of them is dv is dx, so it's not so clear. We did this one, but I used a different, I think, x squared cosine x, I think, is what I did. And because of the squared, we had to repeat the integration by parts twice. So that's an example of repeated integration by parts. And then this next one, last one we're going to be able to do today, is what I call pulling a rabbit out of a hat, which is kind of like magic. So here it is. And Mohammed, you get to give me a number between 1 and 12. 7. Let's push the limits here. That's an alpha in front of x, and that's a beta in front of x. And you said 7? 1, 2. I'll start from the bottom this time. 1, 2, 3, 4, 5, 6. And it's lucky Stephanie. I'll give you a hint, Stephanie. It's integration by parts. But more importantly, I want you to think about, Stephanie, this whole transferring of the derivative, right? That one of them gets differentiated, the other one gets integrated. Do you kind of see what the problem is going to be if you try and use integration by parts here? What do you see happening? Like if you choose one of those to be u, I didn't mean to do that. The derivative will be itself, right? Yes? Like if you choose u to be the e to the alpha x, then the derivative is itself, and you'll have an alpha pop out because you're differentiating, chain rule. And when you integrate that, right, you're going to get a sign, aren't you? So your new integral, the diagonal, is going to have an e to the alpha x and a sine beta x, isn't it? And that's no better than this. And if you do integration by parts again, the same thing's going to happen. See, nothing's going to get nicer. Do y'all see that? Nothing's ever going to get cleaned up. But it's going to work. And it's not obvious why, and this is the magic, okay? So here we go. You got to pick a u and a dv, so go ahead. Okay, u is going to be e to the alpha x, and that only gives you one choice for dv. What is it? Cosine beta x dx, yeah? All right, let's take a derivative, Stephanie. What is the derivative of e to the alpha x? Okay, don't forget, what's the derivative of alpha? That just turned black, right? That's the magic, yeah. What's the derivative of e to the alpha of x? It's e to the alpha of x, but then you have to take derivative of alpha x. Alpha is a number, like 4x. If I say, what's the derivative of e to the 4x? You say itself, right? Times derivative of what's up here, which you would say 4, right? Derivative of 4x is 4. But instead of me giving you a number, I'm saying it's alpha. So it's going to be alpha. So we're going to have, the alpha is going to pop out when we take the derivative. So I'm going to put it in front. Alpha e to the alpha x dx. Everybody follow? That's the derivative of e to the alpha x. Now, Stephanie, antiderivative of cosine beta x. We're going the other way now. We're going antiderivative. So I agree with this part. 1 over beta out front. It'll work both ways. It works both ways. The question was, would it be easier if we would have let u be cosine beta x and let dv be the e to the alpha x? And it turns out for this problem, it works both ways.
Because then you would just get 1 over alpha, right?
Where?
Do it the other way? You're integrating it? E to the alpha x?
If I put e to the alpha x here, and I integrate it up, I get 1 over alpha e to the alpha x. But I'd still have another trig thing here, and when I go diagonally, I'm still going to have the same thing. I'm going to be pretty much stuck in the same boat. Does anybody need any clarification on this setup? Okay, let's apply the formula. Ultraviolet. And Stephanie, please give me all constants out front, please, first. Okay. And then, okay, good. Okay. Minus. Now, I don't know how far you want to push, but would you like to pull constants out before I write the integral down? Because that's kind of where you want to get, where you don't have to write it twice. Think about your diagonal here. You're going to have a 1 over beta, right? And an alpha, and that's coming out. So I should put minus what? Alpha over beta, right? That's the same as alpha times 1 over beta. Integral. Ew. I should do sine beta x times e to the alpha x dx, right? But I'm going to switch the order because it's multiplication. Really doesn't matter, right? And that should be a beta. Dx. All right. All of that, and we really didn't gain anything, did we? We started with an integral that we couldn't do, and we ended with an integral we couldn't do. But I told you to trust me here, that it's going to work. You're going to need to apply integration by parts again. All right? Let's do it again, and then you're going to see the magic. All right? So I'm focusing now all my attention on just this integral right here. All right? And I think I'd like to knock off another student here. So Stephanie, are you okay if I move on? Okay, you want to keep going? Yeah? Okay, keep going. All right, so now just that in purple is a new problem completely separate from this, right? It's like I have my own little scratch work over here. I'm not worried about trees. The planet's fine. And set up my new integral. I'll even write it down again, right? If you want.